So, in this tutorial, I will explain a little bit how we find differential expression genes using the limma package of R. So this is the class BIOL476. It's 26th of March. The class is the analysis of genetic data. So in the previous class, we saw how to find genes that are differentially expressed using the function lm. And this stands for linear models. And for example, we saw that using lm, we can model the expression level of a gene as a function of some parameters, for example, as a function of a condition. So if the condition is healthy or disease, and this is the only parameter that may affect the expression level of a gene, then this means that if we have a gene or an individual I, the expression level of this I individual will be an intercept. Let's call it alpha. This is the intercept. Plus beta multiplied by x, where x will be either 0 or 1. It will be 0 if it is, for example, healthy, given that the healthy is a reference level, and it will be 1, x will be 1 if the individual I comes from the disease group. Plus some epsilon term, which is the error, which means this epsilon comes from a Gaussian distribution with mean 0 and some standard deviation. Therefore, if the individual is healthy, then this x will be 0. Therefore, the expression level of this individual will just be alpha plus epsilon. This means that the expression level of this individual will be around alpha here. So these are the healthy individuals. And if I is an individual from the disease group, then in addition to this alpha, the expression level will have this beta term. So this will be beta, for example, and here will be the predicted expression of these individuals from the disease group. So these are the guys from the disease group, and these are the guys from the healthy group. Now, these two groups are different if this beta thing is statistically different than 0. So the null hypothesis here is that beta equals 0, and using all the statistical framework, we examine whether we reject or not the null hypothesis. Similar idea applies when we use this limma package. So this is what we have done already. Now let's go to this limma package. And in this limma package, the important things are some concepts here. We need the label vector, which simply will describe in which group every individual belongs to. And then what is needed is the design matrix, which will give us the structure of the experiment. In other words, this will give us for every individual where it belongs, plus the parameters that are important for us to model the expression level. So here is where each individual belongs. Plus the parameters, the factors actually. For example, if the individual is healthy, so the condition is here like the condition of individual. This is important for our experiment in this case. And then we will apply 3 or 4 functions. One is the lmFit function. I will explain later what it does. The makeContrasts function. I will see later. So these here are the functions, important ones. So it's the lmFit function, the makeContrasts function, the contrasts.fit function, and the ebase function. So these are important functions for the statistical analysis using this limma package. So let's start from number 1, the label vector. And in order to explain all this, maybe it's better to go directly to the R code and explain what, and I will go back and forth between the nodes here and the R code. Okay, so let's start from the beginning. It's an easy example. So first, you see whenever we run something in R, perhaps this the memory of the workspace is full, maybe from other scripts that we have written. The problem with these objects here is that they are also shared in the script that we write. Therefore, it's possible that we'll do some calculations, but it will not use the objects that we have defined here, but another object with the same name from another script. Therefore, a good advice is always to clean the memory using this line here before we start the script. You see that the environment is empty now, and now I define a matrix which will represent the expression data. So the experiment is the following. We have a matrix that represents the expression data. As far as I see, in this matrix we have 100 genes, and we have 50 samples. Out of those 50 samples, the 25 are healthy, and of course the 25 come from the disease group. And then I define two means, two variables m1 and m2. These represent two means that we will see later on. One is 100, so m1 is 100, and m2 150. And in the beginning, I create a matrix with all genes and all samples here for all genes and for all samples. The expression level comes from a Gaussian distribution with mean m1 and standard deviation as t. So this will be m1 10. So these are 100, as you will see later on. But then for the first half genes and for the first half samples, I assume that the expression level comes from another Gaussian distribution with mean m2. So actually this is 150 and this is 100. So this is m2 and this is m1. So this is the experiment. Now, for all these genes here, actually the H0 is true because there is no differential expression between the expression level here and the expression level here. But for these 50 genes, the null hypothesis should be rejected. The alternative is true actually, because the expression level of these guys is different than the expression level of these guys. Okay. Now at the beginning I just make a heat map to see how this matrix looks like, and you see the heat map here. Indeed, the expression level of these guys is much higher than the expression level of these guys. Whether for these genes, these 50 genes here, the expression level between these two groups is exactly the same. Okay. Now, the first thing that I do is that I set, as far as I said, here, I need to go here, the label vector. So this label vector is a vector of class factor and denotes for each sample in the order of this matrix. So for every sample, which is represented by a column here, so for every column in this matrix where the sample belongs to. So the first 25 samples belong to the healthy category and the next 25 samples belong to the disease category. And what I'm doing here with these levels argument is that I set that the default condition will be the healthy one, which I will use later on as a reference. Okay, it's nothing else than a vector, but it's not a string vector or a numeric vector, it's just a factor vector. We have factors when we want to model a variable that is discrete. In other words, this is not a variable like numbers. There is no order here. It's not that h is before d or d is before h, or that h is greater than d or whatever. It's just a variable. The label is a variable that is discrete and without order. It's a nominal variable. And it has two levels, h and d. And here we just said that the h will be the first level, but no order is implied here. But because we will use this h as a reference later on. Okay, for the rest of the analysis, what we need is this limma package. If it's not installed, you should install it using these lines. These lines comes from the BIOContractor. So we need to use BIOContractor in order to install limma. And then we load it. And the first thing that I'm doing is that I convert our matrix to a data frame. This is usually not needed when we analyze real data, because as you will see later on, when we read real data using some special commands far, the object that will be produced will be directly data frame. But in this case, A was generated as a matrix using the matrix function here. Therefore, I need to convert the A to a data frame using this as data frame function. Okay, I must run, of course, I must run this code. Probably I didn't run it. Okay, let's start from here. Okay, and now limma, the A has been modified to a data frame, and the first thing is to see the design matrix. So as far as I said earlier, the design matrix reveals the structure of the experiment. In other words, it says where each individual belongs to and the important parameters for modeling the expression level. So this is the design matrix. And you see that there are two important parameters here, the intercept and the label, the D level from the label condition, from the factor label. So this name here, label D, comes directly from this vector, which describes the category of each individual. Since I used the H as a reference, the design matrix here will have all the other levels but the reference. And you see here that in order to create the design matrix, I use the function model.matrix, and then what I say here is that I want to describe the expression level of all genes. This is the tilde. I'm going to describe the expression level of each gene using the factor label. Therefore, the label comes here as a name in a column of the design matrix. The label has two levels, the H and the D. The H is a first and it's a reference, and therefore the second one or any other one will be here in the design matrix. So these are the two columns, the intercept and the label D. If you want to see that graphically, these two columns represent these two parameters, the alpha and the beta. The alpha is the intercept and coincides with the expression, the average expression level of the healthy group, and the beta here is the difference between these two expression levels. So in our case, the beta is the D, this D here. And because these names are a bit long and ugly, here I change them to intercept and D. Call names design, I modify the names of the columns of the design matrix. Okay. So what this matrix tells us? this matrix says the following. If you want to model the expression level of the first individual, so here if this I is the first individual, so we have the y1, then what you should do is to consider the following. Let's put another parameter here. Let's put the parameter, we have x here, and let's put the parameter L here. So L will take two values, 0 or 1. It will take 1. The value that L will take here is whatever exists in this column. Okay, so what it says is that if you want to model the expression level of the first individual, then put 1 at the L and 0 at the beta. At the X, sorry. 1 at the L here and 0 at the X here. Therefore, the expression level of the first individual will be alpha multiplied by 1 plus beta multiplied by 0 plus this error term, which is this Gaussian distribution. Thus, y1 will be alpha plus epsilon, which means that the expression level of the first individual, let's say that it's this one, will be around this alpha value. Similarly for all the first 25 individuals here, but then at the 26th individual, which is the first individual that belongs to the disease group, we have the following. We have n1 here, which means that the expression level of an individual here will be, let's say this 26, will be alpha multiplied by 1 plus beta multiplied by 1, multiplications here, plus epsilon. Therefore, the expression level of this individual will be around the alpha plus b. Alpha plus b is actually here, so it will be around here. So the function lmFit, what it does, lmFit, sorry, is that it finds out, okay, let's start writing here. So the function lmFit, which is the first function that we need, it calculates, it infers from the data the values of this alpha and beta. Or in our example here, I remind you that our model says that the expression level is alpha plus beta x plus epsilon. In other words, the alpha is the intercept and beta is this factor here, is the difference between the healthy and the disease. Okay, so this lmFit will just find out that these two values, this one and this one. And let's say that we'll find that alpha equals 150 and that beta equals minus 49.9, let's say something like that. Which means that the healthy guys will be here at 150 and the disease guys will be here around 100. And this one will be minus 50, about minus 50, minus 49, let's say, something like that. Okay, is this enough? No, it's not enough, because what we care actually is not to find out the value of this. We care about it, but it's not the only thing that we care about. What we actually care is to show or to examine whether this beta is 0 or is statistically different than 0. So if we can reject, if we have the null hypothesis, or if we can reject the null hypothesis. If we can reject it or not. We cannot say that the null is correct or the null is wrong. If we would accept that it's correct, so if we can reject it or not. Okay, so lmFit, the only thing that does is finding out inferring the values of this alpha and beta, but this is not enough. We want to see if this value here is statistically different than 0. We have the null hypothesis at 0, and in order to find out whether it's different than 0, then what we need to compute actually, this is the most important thing in our analysis, is to compute the variances, which means the uncertainty that we have regarding this inference here. In other words, if the samples around these inferred values will be like that and like that, then our certainty is huge, because there are values here that are very far away from this inferred value, and there are also samples here, expression levels in this disease group, that are very far away from this value. However, if the values would be like that and like that, then our uncertainty is much, much smaller. Okay. So in order to quantify this uncertainty, we need to learn something about the variances, the total variance here. And this analysis that we do with the lmFit and the contrast assumes, and maybe this is a drawback of all this analysis, that the variances here are more or less the same. They are not dramatically different between these two groups. So it's not that we have in the healthy group something like that, and the disease group something like that. More or less they should have the same variance. Not strictly the same, but more or less the same. We'll see later on that the bias function that we use at a later step here remedies a little bit this assumption. Okay. So in order to study the variances, we will use this function here, the contrasts.fit. But before that, we should make the contrast. And I will explain now what the contrast is. We saw that in the design matrix here that we have two parameters, the intercept and the label D, or the alpha and the beta. Not both of them parameters are interesting for us. We don't care, for example, about this level, which is alpha. We only care about this difference, which is a beta. The contrasts, the concept of the contrast is actually the following. which parameter, we should define here which parameter we want to study and to apply the hypothesis testing. So for which parameter we want to test whether we should reject or not the H0. And in our case, the only parameter that we're interested in is a beta. Because the null hypothesis says that beta is 0, but there is no difference between these two groups. So from the design matrix, this parameter is the D. Remember that I changed the names here because I didn't like the label D. I make it to be intercept and just D here. So the design matrix in my case has a bit smaller names, intercept and D. And I'm interested in the parameter D to see if this D is 0. Okay. So this contrast is nothing else than a matrix that defines the following. What I want to study here is actually this column. This column is the important one. I want to study whether the intercept multiplied by this value plus the D multiplied by this value is statistically different than 0. So if I will multiply intercept by 0 and D by 1, what I will get, of course, is just a D here. So what I study eventually is that D is or is different than 0. Write it down again. So we have the contrast matrix, which is this one, and it writes that intercept has a coefficient of 0 and the D has a coefficient of 1. And what I'm interested in is the intercept multiplied by 0 plus the D multiplied by 1 if this is or is not different statistically than 0. This is the null hypothesis. It's a fancy way to say that D equals 0 is the null hypothesis. In other words, that this difference here is 0 is the null hypothesis. Okay? And then what we do here is that is the following. We use the values that we have estimated using this lmFit, which is the alpha and the beta, the intercept and the D in our case. And we say here using the argument contrast, which is this previous one, what we are interested in. So notice that here we override this fit object by this analysis because here we exactly study whether the null hypothesis, as I described it earlier, holds or not. So after this function, we don't care any longer about the inference of alpha and beta. We just care whether these variables that are interested for us, this D here, is statistically different than 0. So we don't need this fit here, that's why I overwrite it, but we just need the results of the analysis, whether the parameters of interest are different than 0 or not. Okay, I run this function. Probably I should write this. I should run this. I run this. I run this. Now I run this. Now, the important thing, as I said, for this analysis is the estimation of variances. I could have finished the analysis here, but the analysis of variance, the examination of variance is so important, which means that if I don't estimate correctly the variances, then maybe I will have a problem in my results. A problem means that I will have a large amount of false positives or a large amount of false negatives. Plus, all this analysis, as I said earlier, assumes that the variances between the two groups is the same. The next function, this base function, what does is it tries to remedy this assumption and calculate the variances a little bit more accurately. So this is a funny function because what it does is the following. So remember that we have this experiment here. We have a matrix with several genes, 100 here, and these two conditions. And what this base function will do, this one, is that it will re-estimate the variances for each one of the gene using information from other genes as well. And with this way, the estimation of the variances will be a little bit more accurate for every gene. So if a gene will have a very high variance, it will make it, the inference of the variance will make it a little bit lower, because it will say that, okay, I see very high variance, but I don't believe this very high variance. It might just happen for this gene. Just for the specific sample that we have, it happened to have high variance. And therefore, the actual variance might be a little bit smaller. And contrary, for genes that have very low variance, it will say, okay, I don't believe this very small variance. I think that the variance should be a bit larger. So it just happened in this specific sample that the variance is very, very small. So this e-base will use the information from all genes to estimate the population variances. It will be a little, not the sample variances, but the population variances. And here we don't actually override this fit object, because what e-base does is that it provides additional information to this fit object. So this fit object goes here, and this one is not an overwritten fit object, is this one that was here plus this additional information for the variances. That's why we can use the same name. Okay. So the analysis actually has been completed here for all genes, and the only thing that I'm doing with this top table is to see the results, to visualize the results in a table format. And the table format looks like this. This n, first of all, this n means that, okay, give me the results for the first 100 genes. The results here will be ordered by, and it will start from the gene with the lowest p-value, and will end up to the gene with the highest p-value. Okay, here it is. This matrix has the following labels, the following columns. Log of C, I will explain what it is. Of exp, I will explain what it is. This t, this p-value, this adjusted p-value, and this beta here. It's an extra column that does not fit in this space here, that's why R writes it down here. Okay, let's start with the easy things. Log of C originally means log fold change, but here we don't have a log fold change between these two conditions. So I will say what original means. Originally, log of C means the following, but it's not applied in this case specifically, right? So log of C means the following. Log of C stands for log fold change. which means the following: if the expression level of the first group is, let's say, this is the first group, the group A, and this is the group B, this is the health and this is the disease. If the expression level here is 10 and the expression here is 20, the average, log FC will mean that log 10 divided by 20, this is log 0.5, and for this will be, this is actually log 2, this is log 2 1/2, and this will be log 2 to the -1, and of course this is -1. In our case, it's not this number here. In our case, it's just that, in our case, is the difference between the average expression level of these two groups. So in our case, this would be -10. 10 minus 20 minus 10. The name log FC has been kept there because the same function applies to other experiments where actually the log is calculated. But in our case, we don't do that. So what we see here is that for this gene number 16, the expression level of the let's say what of the disease group compared to the healthy group is -58. So this -58 is actually this difference, the difference this one minus this one is -58 in this specific gene, and this is gene number 16. The average expression for all these guys, this and this, is 123. Then we have this T column, which in our case is -20 for the gene number 16, which is similar to the T statistic that we have learned in earlier lectures. So the T is actually a moderated value of a T statistic, or a modified value of a T statistic. Remember that the original T statistic has μ1 minus m2, and here it has some denominator which has some variances, standard deviations. This is the original T statistic, and B here. In our case, the denominator is the same, something like that, which, notice that this is actually this value here, is log FC. But the denominator comes from the base thing. It's this modified variance that we calculate for the experiment. Okay, so this is the T. Then we have the p-value, which in our case is here you see that's a very, very small number. So this means that we reject the null hypothesis that this number is 0. Then we have the adjusted p-value, correct for the multiple testing. We haven't talked yet about it. And then we have here the B value, which is like a score, how much we believe that actually this the alternative hypothesis is correct. The larger the value, the greater, but I don't think that there is a cutoff value that we say that above this value we believe that the alternative is true. Now, what it's obvious here is that for all this, for the first 50 genes, so you see the indices here are greater than 50. Sorry, for the first 50 genes, yeah, the indices are less than 50. The p-values most of them are small here. All of them actually are very small. Minus 53, minus 59, all of them are very, very small. So all these 50 first genes reject the null hypothesis. Contrarily, the p-values of these guys here, maybe with some small exceptions, this guy or these 2-3 guys here, the p-values are quite large. You see that here, 2.6 by the 10 to the minus 1, this is 0.26, 0.27, and so on. These guys reject the null hypothesis, even though they should not actually, because there is no differential expression for these genes. It's actually some genes belong down here. So these guys here are false positives actually. So this is the analysis for today.